You see it everywhere, right? Plastic waste. It feels like this massive, overwhelming problem. But what if the solution wasn't some huge, clunky machine, but something so tiny you can't even see it? Yeah, let's get into that. Okay, first things first, let's just try to wrap our heads around the sheer scale of this. Every single year, we're churning out over 400 million tons of plastic waste. I mean, that number is so huge, it's almost meaningless, right? It's a mountain of stuff that, well, it just doesn't go away. And here's the part that really hits you. Out of all that plastic, take a look at how much we actually recycle. A measly 9%. Just 9? That means 91%, the vast majority, is ending up in landfills, getting burned, or, just trashing our oceans and landscapes. It's just not sustainable. So to make this global problem feel a bit more real, let's zoom in. Let's bring it right down to the local level and see what this crisis actually looks like for a place like Indonesia. So get this. Back in 2021, Indonesia alone generated 11.6 million tons of plastic waste. That's 17% of all the country's garbage. The only thing they throw away more of is food. And the key thing to remember is this isn't a static problem. It's getting bigger every single day. And the environmental cost, it's huge. At least a fifth of all that plastic, 20%, is leaking out into the wild. It's choking rivers, it's polluting the coastlines, and that right there is exactly why we so desperately need to find a better way to deal with this. Okay, so what have we been doing about it? How have we been trying to push back against this tide of plastic? Let's take a quick look at the tools we have in the toolbox right now. So basically, it boils down to two main strategies. On one hand, you've got thermal recycling, or pyrolysis. Think of it as the brute force method, using super high heat, like 400 to 700 degrees Celsius, to just melt plastic down into fuel. On the other hand, you have mechanical recycling. This is more physical, shredding it, melting it, and then squishing it into new things, like those eco bricks you might have heard about. And this is what that mechanical process looks like in the real world. You're looking at a shredder in Palembang, Indonesia, just munching through plastic waste. This is step one for turning that trash into building materials. It's a really hands-on, practical way to handle waste on a local level.
But, and this is a big but, these methods aren't perfect, not by a long shot. That heat-based method, pyrolysis, it eats up a ton of energy and can pump out some nasty byproducts. And mechanical recycling, it usually leads to downcycling. That means the new plastic just isn't as good as the original. And here's the real kicker. Neither of these methods actually gets you back to the pure original stuff the plastic was made from. They don't truly close the loop.
Okay, so this is where things get really interesting. We're about to shift gears completely, away from the world of giant machines and intense heat, and into the microscopic world of biology. We are talking about a tiny, tiny revolution, powered by what you could call nature's A-team of recyclers. The big idea here has a fancy name: enzymatic depolymerization. I know it's a mouthful, but the concept behind it is actually super elegant and simple. All it means is using enzymes. Think of them as nature's little robots to do the work. These enzymes act as catalysts that can lock onto a specific type of plastic and just snip apart its long, complicated chains, breaking it all the way back down to its original, pure building blocks. We call those monomers. So how does an enzyme actually eat plastic? Well, the best way to think about it is like a pair of molecular scissors. So step one, an enzyme, let's call it PTase, latches on to the surface of some PET plastic, the stuff your water bottle is made of. Step two, it starts cutting. It just zips along those long polymer chains, snipping them apart. Step three, as it cuts, the original building blocks of the plastic are released. And finally, the best part, step four, we can collect those pure building blocks, those monomers, and use them to make brand new top quality plastic. It's a perfect closed loop. And this chart, this really says it all. Just look at the temperatures. Pyrolysis needs furnace-level heat. We're talking hundreds of degrees. But the enzyme process, it works at temperatures that are, well, barely warmer than a nice day outside. That massive difference has huge, huge implications for how much energy we need to use. So let's just recap the advantages here, because they're pretty amazing. First, the energy savings are massive, thanks to those super low temperatures. Second, you get pure, high-quality building blocks back, which means you can actually do true bottle-to-bottle recycling, over and over, without the plastic getting worse. All of this gives it the lowest carbon footprint out there. And maybe the coolest part? These enzymes are picky.
They're highly selective, so you can program them to go after just one type of plastic, even if it's all mixed up with other stuff.
Okay, I know what you're thinking. This sounds almost like magic, right? And while the potential is just enormous, we have to be real. We're not quite there yet. So let's talk about the path forward, the challenges we still need to solve, and the incredible work being done to get us there.
The biggest hurdles right now are pretty practical. I mean, how do you take something that works in a little lab beaker and scale it up to handle millions of tons of waste? That's a huge challenge. The process can also be kind of slow, so scientists are trying to find ways to make these enzymes work faster. And while they're fantastic at breaking down plastics like PET, a lot of other common plastics are still too tough for them to crack. So what's on the horizon? Well, this is where it gets really futuristic. Researchers are bioengineering brand new super enzymes designed to be faster and more powerful. People are even using AI to sort plastic waste with incredible accuracy, so the enzymes get a nice clean plate to work with. And we're even seeing these clever hybrid systems, where they use a little bit of chemistry to soften up the plastic before letting the enzymes go to town. And that brings us right back to where we started. We began with this gigantic planetary scale problem, mountains and mountains of plastic waste. And we've ended up looking at a solution that works on a scale so small it's hard to even imagine. The road from the lab to a global solution is definitely still a long one, but it leaves you with a really powerful question, doesn't it? Could these tiny, microscopic biological machines really be the key to solving our massive, colossal plastic problem?